Welcome to Lesson 2.3, Data Visualization. Visualization is often the first step in data analysis tasks. Why? One of the most effective data analysis computers on the planet is right between your two ears. That's right, I'm talking about your brain. Your brain is a data analysis computer that has been fine-tuned over millions of years of evolution to take in and process huge amounts of data from its 5 sensor systems and to recognize important trends such as the behavioral patterns of wild game or features of poisonous versus nutritious plants. However, the brain as a computer is accustomed to receiving a certain kind of input. A modern digital computer loves getting large arrays of numbers as input to analyze. The human brain, on the other hand, is accustomed to receiving rich data in a format that can be seen or heard. The visual system is especially dominant, accounting for roughly 30% of the brain's total volume. A fundamental step in data analysis is figuring out the best way to visualize the data so that you can understand it. Oftentimes, visualization is the most critical step in the data analysis process. This step permits a data analyst to gain an intuition about trends and relationships in the data, and permits a competent data analyst to make an informed decision about the types of analysis algorithms that are appropriate to apply to the data set. It is because visualization is such a critical step in successful data analysis tasks that a significant portion of our first lesson is dedicated to data visualization. What we will see is that there are many ways to visualize data, each with pros and cons, that relate to the types of trends and relationships in the data that our brain can understand when presented with that data representation. This is one of the areas where MATLAB as a tool really shines. It provides a fantastic and extensive set of easy-to-use tools to visualize data in different ways. By the end of this lesson, you will have experience using the most widely used data visualization methods and will understand the methods that are the most useful and appropriate for different types of data sets. So let's go to MATLAB to look at a number of common ways to visualize an example data set. Let's revisit MATLAB's Fisher's iris data set. Recall from our previous section that this data set includes 150 samples for which we have 4 feature measurements in a measurements matrix called MEAS. For each sample, we also have a species label. We can see in species, we have a number of different samples from 3 species of irises. So in reality, we have 150 samples of a 5-dimensional data set where 4 dimensions are petal and sepal measurements and 1 dimension is species. So how can we visualize this data? One thing we can do is print the data set to the MATLAB command window in a more pleasant and customized format than the default format MATLAB uses to print out variables. This is where our friend fprintf comes in handy to let us do formatted printing to the screen. Let's try to print the information about the first sample. We first state the species by printing a character array using the %s formatting operator. Recall that the % tells fprintf we want to supply a piece of input data that's going to be inserted here in the string. And the s tells fprintf that that piece of data will be a character array. The s is actually shorthand for the term string. String is just another name for a character array. Going forward, we'll use the term string and character array interchangeably. Then we include a carriage return to a new line with \n, followed by a tab indentation using \t. Then we print our features. To do this, we'll use the %f formatting operator. The % again tells fprintf we want to insert a piece of data in the string at that location. And the following f tells fprintf that that data will be a floating point number. The following arguments tell fprintf what data to fill in the locations where we have formatted data operators %s and %f, which would be the first species, and all columns of the first row of the measurements matrix. Note that we have 4 %f's, so fprintf is being told to print out 4 floating point numbers. And we also have 4 columns in the measurements matrix. So by supplying the first row of the measurements matrix as the last input to fprintf, we're telling it we want to print all the columns of the first row of mesh. Oops, what happened? We did something MATLAB does not like because it threw an error, which says fprintf cannot take inputs of type cell. Recall when we index a cell array with parentheses, MATLAB returns the cell at that index. A cell data type is essentially a container for other data types, and fprintf doesn't know how to handle such data. What we wanted was to return the contents of the first cell in the species array, which is a character array, rather than return the first cell itself. Remember how to get at the contents of a cell in a cell array? That's right, we use curly brackets rather than parentheses. Also recall that if we want to edit a previously executed command, we can hit the up arrow on our keyboard and bring up prior commands on the command line. That way we can edit and re-execute them rather than having to type the whole line again from scratch. There, now we have our curly brackets. Okay, great. We can see we start on the first line, print out the species. Then we go to a new line, include a tab indentation, and then print out the line with the feature information. Well done. But we can still improve things. We don't really need 6 decimal places in our numbers because in this data set we only have significant digits to 1 decimal place. If we want fprintf to give us just 1 decimal place, we can put a 0.1 after the % and before the f. Okay, so now we have the correct number of digits, but our numbers are so close together that they're difficult to read. If we want fprintf to add enough spaces with the number to ensure that it takes at least 5 characters, then we add the number 5 after the % and before the 0.1. Okay, the format for the first line looks nice, and it's easy to read now. So let's print the whole data set this way using a for loop. We loop variable I from 1 to the length of the measurements matrix, and we print the same information that we printed above. But instead of using the first entry of the species and measurements matrices, we are going to print out the ith entry in the data set for each ith iteration of the for loop. Whoops, what happened? So the first line looks correct. We state the species, then we go to the next line for the features. But then immediately after the last feature, the word species is repeated. We forgot that new calls to fprintf will start printing right where the previous calls left off. So if we don't include a new line or a space, it will start printing right after the last feature. we should just include a new line, \n, at the end of the fprintf string. Let's try that again. There, we'll put a \n there and rerun our loop. Okay, now we can see each independent sample quite cleanly. But it's kind of difficult to tell which sample number we're looking at. And the new line between the species and the features is actually making this twice as long as it really needs to be. Let's include the sample number, species, and features all in the same line. So since the sample is an integer number, we use the D identifier to let fprintf know that we want it to print an integer. And we have to supply the integer I as an input to fprintf. We can also use minimum character counts on our sample number. So by putting a 3 here, we're specifying the sample number should take up at least 3 spaces. We can do the same thing for species and mandate that species takes up at least 10 spaces. And then we can remove this \n and \t to ensure that the features pop up on the same line. By doing this, all of our fields are going to be lined up vertically to make them easy to read from one line to the next. This is nice because we have all of our data in one place in a nice, clean, easy to read format. Having our data set printed in an easy to read format has its advantages. For example, if I want to know what is the value of feature 3 for sample 19, I can go right to it and see that it is 1.7. We can also gain an intuition about the extent of the data set and easily see whether there is any messy, missing, or certain kinds of outlier data. But it also has disadvantages. As humans, we aren't great at looking at a long list of numbers like this and seeing if there are any trends in a feature or relationships among features, or whether the numbers tend to group together or are distributed in some other way. We're accustomed to visualizing the process itself rather than measurements of the process. So, our next task is to see if we can visualize the data set other ways using data plotting techniques. Let's try to plot the first feature vector for the first species, Setosa, which corresponds to the first 50 out of 150 data points. First, we open a figure window, figure 1. Then we call plot and ask it to plot the first 50 rows of the first column of our mesh matrix. Well, that's an interesting looking plot. MATLAB is plotting a curve that's bouncing up and down for 150 data points. What does this plot show us? Well, we can see on average that this feature has a value of around 5, and it ranges from about 4.3 to 5.8. That's useful to know. What about the shape of the plot? Is the shape of this plot useful information for us? Not really. It turns out that for data that are not a function of time or are not necessarily ordered, plot may not be the best choice to visualize the data. Plot by default assumes that the order of the data in the vector we're plotting is meaningful. Thus, it connects each sequential data point with a line segment. However, in our data, each row corresponds to an independent sample. Thus, the ordering of the data points have no inherent meaning. If we instead ask plot to use O's for plotting instead of lines, then we see each individual data point. This removes the connections between the data points and demonstrates another plotting tool that's useful in some scenarios. But here, on the x-axis, the data are still ordered according to the order the data are presented in the vector. Since with our data set, we assume these 150 measurements are independent, the row in which each measurement is located does not have meaning. What would be more informative would be to visualize how the data are distributed in terms of values, regardless of how they are ordered. A common way to do this is to compute a histogram of the data set. A histogram is a way to visualize data that shows the number of occurrences in a feature set on the vertical axis for each range of values of a feature shown on the horizontal axis. The tall bars show us there are many data points of this feature in the specified value range. Low or zero bars show us there are few or no data points that fall in that range. This provides a visually intuitive representation of the distribution of the data, including the range, average, or median values, and how much the data vary from the average or median. Histograms and other functions of data distributions do not assume there is any meaning in how the data are ordered, but rather rely on the number of occurrences of different values in the data set. So, no matter how I order a specific list of numbers, this histogram is always the same. Another common way to visualize the distribution of data in MATLAB is the box plot, which we saw in the last lesson. Okay, let's check out what histograms of our iris data look like in MATLAB. To display a histogram of the first 50 data points of the first feature in MEAS, we just use the histogram function with the first 50 rows of the first column of MEAS as input. We can also label the x-axis as corresponding to the feature value, and the y-axis is corresponding to the number of occurrences. We can see that the histogram function groups the 50 data points into 6 bins, as shown with the width of the 6 bars on the horizontal axis. The height of the bar corresponds to the count, or the number of occurrences of a data point within that bin. So with this visualization method, we can quickly and easily see that the data range from about 4 to about 6, with an average of about 5. And in fact, we can see that we have a total of 20 measurements of this feature that have a value between 4.8 and 5.1. Now that we're armed with this knowledge, when we go back and look at the values of our first feature in a printout of the data on the screen, it's fairly easy to see many instances where this feature takes on a value between 4.8 and 5.1. MATLAB uses an algorithm to determine the size of the bins that are used by default based on the dataset we provided. However, if we would like to use a specific bin size for the histogram, we can supply that information as a second argument to the function. As always, type help histogram for more information about inputs and outputs of a function. As shown in the help information, we can supply a vector as the second argument that contains the quote edges of the bins we would like to use. We'll try out that functionality in a few minutes. First, what about feature 2? Let's also plot a histogram. we open a second figure window, figure 2. And in this figure, we will display a histogram of the first 50 rows of the second column of mesh. And similarly, we can label the axes. What we see is that feature 2 has its average around 3.5 with a range from about 2.5 to 4.5. So this feature looks a bit different than feature 1, but it's a bit difficult to see that because these histograms are in separate windows. Oftentimes, it's helpful to visualize the data side by side. Let's put a histogram for each feature in subplots of a single figure window. To do that, let's go back to the first figure and create a subplot in a 2x2 matrix of subplots. And we'll show that first histogram. We'll label its axes, specifically for the feature 1 value. Then we can go to the second subplot and plot a histogram for the second feature. And go to the third subplot and plot a histogram of the third feature. And go to the fourth subplot to plot a histogram of the fourth feature. So it's nice having them all in one place, but it's still a little bit difficult to compare them since the feature range and height range of each plot is different. Let's put all 4 plots with the same axes ranges. What ranges do we want? Well, on the y-axis, we can see we need to range from 0 to about 40 to cover the range of number of occurrences across the 4 plots. And on the x-axis, we need a range covering the range of values in mesh. So MATLAB can tell us what the minimum and maximum values are. The minimum value in mesh is 0.1, and the maximum is 7.9. So for each subplot, we'll set the axis to range from just below the minimum value on the x-axis at 0 to just above the maximum value at 8. And the number of occurrences will range from 0 to 40. We'll do the same for subplot 2. And the same for subplot 3 and 4. Now we can really appreciate just how different the distribution for each of these 4 features really is. Now let's repeat this in figures 2 and 3 for the second and third species, which range from data points 51 to 100 and 101 to 150 in our data set. But instead of repeating these blocks of code for each feature and for each species, let's make our code more compact and less repetitive by using nested for loops. So our first outer loop will correspond to the species. So we will loop variable I ranging from 1 to 3, corresponding to the species. For each species, we'll have a figure with figure index I. We can also define the data range for the species. If I is equal to 1, our data range is over the first 50 rows of the data set. Else, if I is equal to 2, our data range is rows 51 to 100 of the data set. Else, if I is equal to 3, our data range is rows 101 to 150 of our data set. Next, we have a for loop for the features. So we have a for loop over j from 1 to 4. For each feature, we'll have a subplot in the figure. We will display the histogram of the jth column of Mej over the rows corresponding to the data range defined in this iteration of the main loop over I. Let's also specify the edges of the histogram bins such that they're identical for all of our histograms. We already know that the minimum and maximum values in Mej are 0.1 and 7.9. So let's define our histogram bin edges to range over 0 to 8 so that we include the entire data range. Let's also define our edge step size to be 0.25 so that the width of each bin is 0.25. We can also set our axes to constant values so that they're identical for each histogram plot. It's a good idea to include a little bit of white space around the data so that it's easy to visually confirm the data range. So we range our x-axis from minus 0.25 to 8.25, and our y range from 0 to 35, which should be wide enough to cover the range of the histogram plots. The title of each plot can tell us the species and feature number. We can also label our axes with our y-axis being the number of occurrences and our x-axis being the feature value. We end our two for loops, and we can see with 18 pretty simple lines of MATLAB code, we can generate 12 histograms covering each feature of each species in our data set. By switching between figures 1, 2, and 3, we can observe differences in how features are distributed for species 1, 2, and 3. We can see that species 1 is quite different from species 2 and also from species 3, especially for features 3 and 4. However, species 2 and 3 have distributions that are quite similar to each other and have a fair bit of overlap between them. Reviewing what we have done so far, you can observe that great care was taken at every step to ensure each piece of data was visualized in an identical manner. In this example, this included choosing an identical bin size for each histogram, and choosing an identical plot range and scale for the x and y axes of each plot. This may seem like a somewhat trivial detail at first, but visualizing different pieces of data in an identical manner is a hugely critical step when displaying data for visual comparison by a human being. An analogy is when we compare an apple and an orange. We would normally have an apple in one hand and an orange in the other side by side. We would conclude these two items are roughly the same in size and shape, but primarily different in color. On the other hand, if we were to display one on a zoomed-in small axis and the other on zoomed-out large axes, we may be tempted to think that the primary difference is in overall size. Another example. If we're comparing an orange and a grapefruit, if we display them scaled to the same size rather than in a common scale, it is difficult to understand the grapefruit is actually much larger, and the casual observer may incorrectly think there is no very obvious difference between the two, especially since the color of the fruit can vary. In a common scale, the grapefruit is obviously larger. The same thing applies to the data we are showing in our histograms. If we want to visually compare two histograms, it is critical they are shown on similar axes with similar bin sizes. When we do not tell MATLAB exactly how we want the data to be displayed, it takes a guess at the best way to display the data and the best axes to use based on the range of the data itself. However, MATLAB does not know that we are also generating other plots that we want to compare to. So, we have to be quite deliberate in how we prepare and tell MATLAB how to visualize the data to ensure that multiple plots we wish to compare are displayed the same way. Now let's consider the advantages and disadvantages of visualizing data with histograms. We see that for each individual feature, it is easy to interpret the data distribution. Further, it's relatively easy to see how the distribution of a feature differs for different species. This is a huge advantage of this visualization method. However, one thing that is very difficult to understand with this visualization method is the relationship between the features. In most datasets, different features are not completely independent, meaning that the value of one feature may be related to another. We would say that these features are co-related or correlated. In this dataset, for example, it is reasonable to expect that the width of an iris petal is probably related to the length of the petal. We would say these two features are correlated. Individual histograms do not account for correlations across features, and so they do not show whether any relationship such as that exists. A different visualization method that does allow seeing such relationships is called scatter plotting. A scatter plot is a 2D plot where we display a symbol for each instance or sample in our dataset. The value of one feature for that sample is the coordinate location of the symbol on one axis, and the value for another feature is the coordinate location for the symbol on the other axis. So we can easily see the value of the two features for each sample in the dataset. If there is a relationship or a correlation between the two features, the value of one feature should be somewhat predictive of the value of the other feature. For example, larger values of feature 1 would tend to happen when the value of feature 2 is also large. This would result in an upward diagonal slope in the shape of the scatter plot. We could also have a negative correlation, where larger values of feature 1 would tend to happen when the value of feature 2 is smaller. This would result in a downward diagonal slope in the shape of the plot. If there is no correlation between the two features, we would tend to have no diagonal shape in the plot. Let's go back to MATLAB now and look at some scatter plot examples. To create a scatter plot between the first two features in our iris dataset, we use the plot function. we can display the value of feature 2, the second column of measure, on the x-axis, and the value of feature 1, the first column of measure, on the y-axis. Well, that's an interesting looking plot. Because we didn't tell plot to use individual symbols for the individual data points, it assumes that we wish to connect the list of xy coordinates we are providing in a sequence with line segments. We want to have an individual symbol at each point. So let's add an O as the last input to plot. This will tell plot to put a small circle at each data point and not to connect the data points with line segments. Looking at this scatter plot, we don't see much of a diagonal feature, and so it doesn't look like feature 1 and 2 are correlated. But before we completely discount this idea that there may be some correlation, let's take a look at the scatter plot when separating the 3 different species. After all, we know from looking at the feature histograms that the different species have different feature distributions. We can show all 3 species on this scatter plot by using a unique symbol for each species. First, we need to separate the dataset by species. In general, when we have a categorical variable, like species is, we can use MATLAB's unique function to tell us what unique entries exist in a cell array. If we use the third output of unique, it provides a vector the size of species that contains, for every entry in species, the index of the entry in U corresponding to the entry in species. This, in effect, assigns a number, in this case 1, 2, or 3, to each of the unique species strings we have in the species array. This is great because numerical labels are much easier to work with in MATLAB than strings. We can easily group together all data points assigned to species 1, those assigned to species 2, and those assigned to species 3 in a more straightforward manner than by checking the values of the strings in the entries of species. Now we can scatter plot the first 2 features using different symbols for each species. For species 1, we include the rows in measure corresponding to S equal 1. And we plot them with red circles, as indicated by the input argument RO. Next, we tell the figure to hold on to the current graphics while we plot more items. Then we plot the second species, which are the entries in the matrix corresponding to S equal 2, and we plot those with green X's. And then the third species, with blue asterisks. Finally, as always, we label our axes. We can also include a legend that defines the species that corresponds to each symbol. The legend function will assume that the symbol of the first thing that was plotted in the figure corresponds to the first input string, The second thing that was plotted corresponds to the second string, and so on. This scatter plot tells a much different story than the first one. We can see that we do have generally diagonal relationships between features 1 and 2 for the individual species, especially for Setosa, but also for the others. This is sometimes maddening, but also a fun part of data analysis. When data are inspected in one way, no relationships exist, but displayed another way, trends are evident. So far, we've only looked at the relationship between feature 1 and 2. This is because with a 2D plot, we only have 2 dimensions, and so we can only accommodate 2 features. But we can repeat our scatter plot method for each combination of different feature values. First, let's observe that there are 6 combinations of features. We can define a 6x2 matrix that contains each feature combination. First, features 1 and 2, then 1 and 3, then 1 and 4, 2 and 3, 2 and 4, and finally 3 and 4. Let's display each of the 6 scatter plots as subplots in a new figure. We'll loop variable I from feature 1 to length C, which is the number of scatter plots that we will create. And we'll make a 2x3 pattern of subplots and plot the ith subplot in the ith iteration of the for loop. We then do a scatter plot for each species as we've done before. Where instead of feature 2, we're going to do the feature in the second column of row I of matrix C versus the feature in the first column of row I in matrix C. And we do the second species with green X's, and the third species with blue asterisks. And we can label the X and Y axes with the proper feature numbers. Corresponding to the indices in our matrix C. And we can also add a legend. Note that if the legend pops up in an inconvenient location by default, we can always grab it with the cursor and move it somewhere else. These plots are rich with information about our data set. For example, consider the Setosa data in the red circles. We can see features 1 and 2 are correlated with each other, resulting in a diagonal relationship. But neither features 1 nor 2 are correlated with features 3 or 4, resulting in non-diagonal relationships. We can see that for the other two species, shown in green and blue, every feature combination has some correlation with at least slightly diagonal shapes, and with some combinations like 3 and 4 being greater than others. We can also easily quantify correlation and detect whether a statistically significant correlation exists between two features. To measure correlation between two features, we use the core function in MATLAB. The two arguments are the same as the two arguments we would provide to a scatter plot. A vector of values for one feature across a set of samples, followed by a vector of values for another feature across the same set of samples. Correlation quantifies whether feature 1 and feature 2 can be related using a linear mapping. That is feature 1 a linear function of feature 2? The first output of core is called rho, often shortened to r. If a good linear mapping is obtainable, the core function returns an r value close to 1. Positive diagonal scatter plots produce r values close to 1. Perfectly correlated data have r equal to 1. If the two features are uncorrelated, that is, feature 1 is not a good predictor of feature 2 by a linear function, r will be close to 0. This corresponds to scatter plots with no diagonal feature. If feature 1 is negatively correlated with feature 2, that is, feature 1 is a good predictor of feature 2 with a negative linear relationship, r will be close to -1. This corresponds to a downward diagonal shape in the scatter plot. The second output of core is a statistical p-value that permits concluding whether the r value is statistically significantly different from 0. Looking at the correlation between feature 1 and feature 2 for species 1, which is shown as the red circles in our first plot, we see we get an r of 0.74 with a very small p-value, much less than 0.05, indicating a statistically significant correlation. This matches what we see in the plot with the positive diagonal shape to the data. Now let's try feature 1 and feature 3 for species 1, which are shown with the red circles in the second subplot. As seen in the plot, we do not have a diagonal shape in the scatter plot, and the correlation function returns a low r value of 0.27 with a p-value greater than 0.05, indicating that it is not statistically significantly different from 0. Typically, a correlation r greater than 0.7 is called a strong correlation. Between 0.3 and 0.7 is considered moderate, and less than 0.3 is considered weak. Our first example is thus an example of strong correlation, and our second one of weak to no correlation. An example of moderate correlation would be the relationship between feature 1 and 2 for species 3, shown in the blue asterisks in the first plot. We get an r value of 0.46. In the plot we can see a diagonal relationship, but the data are very spread out rather than forming a tight diagonal line. This is indicative of a moderate relationship. The correlation function is very useful for comparing two data vectors to quantify if a linear relationship exists between the two. We also see how these plots show us how different species are distinguishable by their feature measurements. If we have feature measurements for an iris and need to figure out what species out of these 3 that it belongs to, we can inspect these plots. For example, a small value for features 3 or 4 implies our iris species is setosa. This also shows scenarios where the relationship between features is important. For example, if we are given that feature 1 is equal to 5, we can see that any species could possibly take on that value. Similarly, if all we are given is that feature 2 is equal to 3.2, any species could also have that value. However, if we were given that both feature 1 is equal to 5 and feature 2 is equal to 3.2, these plots indicate it is highly likely this comes from Setosa versus one of the other species of iris. This brings us to one of the most essential and common data analysis tasks, which is classification. Classification involves the use of one or more features or measurements of a process to determine what type of process is occurring. We will discuss classification in much more detail in a following lesson. Scatter plots are an excellent tool for understanding relationships between features. Histograms or box plots are better for understanding the shape of data distributions. In summary, we find that common data visualization methods each have pros and cons for helping a data analyst understand underlying relationships and trends in the data. You now have experience with the most common data visualization methods in your MATLAB repertoire. One piece of parting advice. Since each visualization technique has pros and cons, it's a good idea to always try to use multiple data visualization techniques to try to get the most complete understanding of your data.